Hi guys, so here's our geometry final exam review. So let's go ahead and start into this. We do need to discuss topic by topic, and it looks like our first one up is parallel lines and transversals. So again, if we're looking at this diagram, we are assuming that line L is going to be parallel to line M, and then that we have this transversal line that cuts through those two parallel lines. Okay. Now, we're going to discuss about congruency based upon what angle goes with what angle. So let's get into the idea of congruency. Now, number one, which angles are congruent to angle 3? So I'm going to go ahead and mark the measure for 3 or the angle 3. And I immediately think of vertical angles. Okay, there's a vertical angle there. So angle 1 would be congruent to angle 3. Also, alternate interior angles kind of kick in right there, and I see that. So again, we have vertical angles for measure 1. And then for measure 8, we have alternate interior angles. So that's the idea there. And I also noticed that angle 6 is also congruent to angle 3, and that's because they are corresponding angles. All right, and we learned about that. Very nice. All right, so number two, what theorem justifies that angle 3 is congruent to angle 6? And how about that? It looks like we already talked about that, right? So that reasoning was again because of corresponding angles. And so that was nice. And then number three, what theorem justifies angle 4 being congruent to angle 5? So if I look at 4 and 5, I'll go ahead and mark them. 4 and 5. Ooh, that's alternate interior angles. Okay, which is basically, sometimes you've seen it like that. All right, what theorem justifies that angle 1 is congruent to angle 6? And that is actually alternate exterior angles. So instead of inside the two parallel lines, they're on the outside or exterior. Okay, so that's where the name comes from. Okay, which is the rarer one to see, but it does pop up. Okay. All right, so what theorem justifies that angle 3 is supplementary to angle 5? And that is actually the same side angles. Okay, and remember, same side are supplementary, therefore measure 3 plus measure 5 has to equal 180. So just be aware of that. Okay. Now, number 6, if the measure of angle 8 is 130, what is the measure for measure 1? Well, that's kind of funny because if you look at angle 8 and at angle 1, you notice they are also corresponding. And like we said earlier, angle 1 is congruent to angle 3, and as is angle 8. So by the transitive property, angle 1 is going to have the same measurement as angle 8. So 100 and, oops, almost put 30. It's 180 or 130 degrees. Sorry, I jumped ahead and started thinking about other stuff. So 130 degrees. All right, if measure 7 is 54 degrees, all right, we got 54 degrees right there. What is measure 5? Well, measure 5, or the angle 5, the measure for angle 5, is really a vertical angle, so it is also going to be 54 degrees, okay, because those two are congruent. Now, if measure 5 was 57 degrees, what would be measure 4? Those are actually alternate interior angles. So if the measure for 57 or for 5 was 57, then measure 4 would also have to be congruent, so the same, and it's, again, alternate interior angles. And that again is assuming that line L and M are parallel, which they say. All right, so number 9, give the pair of angles that form a linear pair. So let me try to do this in a different color, and let me clean up my markings here in my diagram. Um, Linear pair. All right, a pair means two, right? That means they share. So what do they share? They actually share um, sides. Okay, so let me use a bright green, and hopefully that checks out just fine. I notice that 1 and 2 are a linear pair. I notice that 4 and 3 are a linear pair. I notice that 8 and 5 are a linear pair, and 7 and 6 are linear pairs. Okay, so as you can see, there's a lot of pairs there. Now, let me write that out real quick. So, and I'll write it out in this idea that um, angle 1 plus angle 2 um, is the same as angle 3 plus angle 4 plus the measure of angle 5 plus, or I'm sorry, this is equal. Let me clean that up. So fun fact, all of these um, linear pairs are supplementary. That means they all add up to 180. And I have no idea why it's giving me such a hard time to erase. No, get out of my way. And I want to erase that. You know what? I'm going to scroll down because I think it's something to do with that. Oh my goodness. Oh, okay. Got it. Technology. It's okay. Only okay. There we go. And then angle 5 plus angle 8, which should equal angle 6 plus angle 7. And those should all equal 180 degrees. Okay, so that's the idea of linear pairs. Now, another thing to consider is that we actually have more than just those. Okay, linear pairs can also include measures 1 and 4, 2 and 3, 5 and 6, 7 and 8. So we actually have a lot of linear pairs. Okay, so remember, there are two angles that share the same side of a line. We have three different lines. So believe me, we got several linear pairs, not just the ones that I wrote in green, but also the ones I highlighted in blue. So be aware of that. Now, giving pairs of angles that are supplementary, all the linear pairs are supplementary. All right, they add up to 180. So the list from number 9 can also be used for the list for 10. But be aware of same side. Okay, same side like 5 and 3, 4 and 8. And angle 5 will equal the measure for 4 and measure 8. And same sides also add up to 180. So just be aware of same side angles. Okay, lastly, looks like number 11, give a pair of angles that are vertical angles. Okay, good. So let me clean this up because I've been marking this like crazy and using highlighters and just going crazy on all of it. Vertical angles, I'm going to mark them right now. Vertical angles, angle 1 has a vertical angle of 3. So measure 1 would be congruent to measure 3. I notice that the measure for 2 has to be a vertical angle of 4. So we know those have to be congruent. And then same pattern here, 5 and 7, okay, would be vertical angles, and therefore they have to be congruent. And then lastly, 6 has to be a vertical angle to 8. So we would say like angle 6 has to be congruent by angle 8 because they're vertical angles. Okay, so those are the pairs of angles that are vertical angles. All right, so moving on to parallel and perpendicular lines. What is the slope of a line parallel to y equals 2/3 x plus 1? Well, I noticed that my slope here, all right, is 2 over 3. And then my initial value, my y-intercept, is 1, right, my b. So I want to go ahead and say, remember parallel lines have to have the same slope. So the slope that would be parallel to this guy would be the same, all right? So my slope here would have to be 2/3 in order for another line to be parallel. Notice though, you do need a slightly different uh, b value. Otherwise, that would be coincident. They'd be the exact same line. And that's not technically parallel because by definition, parallel lines never intersect. So your b would have to be any other number um, that's not positive 1. Okay, so just be aware of that if you were ever to write an equation. For example, like y equals 2/3 x plus 4. That would be an equation that's parallel, okay, to the equation that we had. All right, so number 13 was the slope of a line that's perpendicular to y equals 3/4 x minus 5. So it's it's not exactly the same. Okay, we have to actually use the reciprocal. So instead of 3 over 4, okay, we actually have to flip it and then negate it. Okay, so we're going the opposite direction. So our slope, again, would have to be -4 over 3. Okay, what's the opposite of going up 3 and then run 4? Oh, it's go down 4 and over 3. It's the exact opposite. Okay, so that would be an example of perpendicular. All right, number 14, what does it mean for two lines to be perpendicular? Well, they would have to intersect at 90 degrees. Okay, so if they were to cross one another, it has to be looking like something like that. All right. Of course, it could be rotated a bit, but it would look something like that. Now, what does it mean for two lines to be parallel? Also, going back to number 14, um, intersecting at 90 degrees, but also that there is at one point, comma, there will exist um, one solution, and that kind of ties into algebra 1 and even algebra 2. Okay, so there's always that conversation. So there's at least one intersection. Now, with parallel lines, all right, parallel lines never intersect ever. Okay, so if somebody's like, hey, we should go on a date, just go, nah, I'm a little too parallel for you. All right, that means you guys will never intersect. Okay. Sorry, math pun. All right, so moving on. Transformations, number 16. What transformation maps on? So we're talking about mapping from ABC onto, again, remember that arrow means onto, A prime, B prime, C prime. All right, so it's basically the red triangle to the blue triangle. Now, if you notice, their positioning didn't really, or their angling didn't really change, just their position. So if you actually look at A, all right, A originally was at 2 comma 3. Okay, and then it moved to A prime. Now it moved to A prime, which was or is now at -3 comma 6. If we look at B to B prime, sorry, that's a terrible B prime. There we go. I don't know why I wrote squared. Just ignore the square. Okay. So we got b, that's at 2 comma negative 2. Then b prime is at negative 3 comma 1. Okay, that's good. Now let's check out c. So I'm being thorough. I'm going point by point. That way I can see it all in the grand scheme of things. And to c prime, negative 6 comma negative 1. All right, so let's talk about what happened. We were at 2, and even if you look at visually, we actually just went 1, 2, 1, 2, 3, 4, 5, 5 to the left, and then we get 3 up, okay? And it should be the same for every single point. So you could always double check 1, 2, 3, 4, 5, and then up 3, 1, 2, 3. So if you notice, this is rigid motion, okay? This is actually a translation. So the name of this transformation is a translation, and by a vector of, and you could always write it like this, we went to the left 5, and then up 3. Okay, so that would be the answer there. You could always double check it with the algebra here. As you can see, we used to write it like this. You know, if you see this on a test, it's the same as writing the vector, but this is actually the rule, so you need to be aware of that as well. So again, x's went to the left 5, they decreased by 5, and your y's increased by 3. Okay, so that's the rule. So you might see that. So be aware of the rules as well. All right. So number 17, what's the transformation? If you realize that the distance from C to C prime is the same across the y-axis, and that the A to A prime is also the same distance from the y-axis, and even if you tested the B to B prime, sorry, that's a terrible line, I know, but the distance here is the same as the distance from here from the y-axis. We are dealing with a reflection, okay? More importantly, a reflection across the y-axis. So that is something to take note, all right? It literally looks like it just flipped over um, the y-axis, all right? So this is a reflection, and I shouldn't say the word flipped. I'm just saying that for the sense of movement. Okay, so this is a reflection. You can always tell because if you wrote the rule, and that's something you need to be aware of, you had, you know, x comma y for your points, but what happened is eventually your x negated, but your y stayed the same. So this is the rule. So make sure you understand the rules as well. All right, 18. Transformation. Whoa, looks like this thing spun around, right? So you were here, right, for your image. Or I'm sorry, your pre-image, and then now you're here at your image. Okay, so it looks like you rotated. All right, if you want to go point by point, you can. So if you went started with A, and that's at 1 comma 1. Then you realize that A prime actually just rotated to negative 1, comma negative 1. You would realize that your rule here, and you could always test your other 2 points, but remember rigid motion, the objects need to maintain distance, preserve distance. So it looks like distance is preserved. The rule would be you have your point, and then your x negates, and your y negates. This is actually a rotation. Okay, a rotation by 180 degrees. So just kind of look back at that. Um, Again, if you were to spin this around, um, either counter or clockwise, it would still end up being where it is. Same thing with B and C for all the points. So again, be aware of the rule as well for 180 degrees. All right, congruent triangles. So number 19, in the figures below, what additional information is needed to prove that these two triangles are congruent by side, angle, side? Okay, so they gave us a side being congruent here with these tally marks. Tally me bananas. They did say these two angles are congruent, probably because of vertical angles. And then what else do we need? Because we need side, angle, side. We got side, angle. Ooh, I would need to know this side being congruent to this side, right? Because they're asking about SAS. And the only way I can spell out SAS without getting sassy is knowing um, the additional information that OQ has to be congruent to OR. Okay, so that's the information we would need in order to get that side, angle, side, triangle congruency set up. All right, and number 20, and what figure, the below, what additional information is needed to prove that these two triangles, ABC, is congruent to triangle DEC by angle, angle, side. Okay, so they mark this side, AB, as being congruent with DE. We got a side here. I do see a vertical angle situation just naturally, right? So I know those two angles have to be congruent. Good old vertical angles. Now we want to be able to spell angle, angle side. There's several ways we can go about this. Honestly, um, you can go with angle B being congruent to angle D, or you could go, okay, because again it would spell out angle, angle side, or as an option, angle A would have to be congruent to angle E. Um, and that would also spell out angle, angle side. So just be aware of that. It's only when you jump over another angle it doesn't work, or another side, just depends. But in this situation, these two situations could work just fine. All right, number 21, same situation. Actually, no. What figures? All right, in the figure below, what triangle congruence theorem proves that these two triangles are congruent? All right. Um, Again, this side is congruent to this side, so we get a side there. We get a side here. Okay, that's so we get a pair of sides. We get this side here being congruent with this side here. And then remember the reflexive property. AC is congruent to itself. Okay, so that works just fine. Now, they didn't tell us it's a parallelogram, so it's not like 100% sure about the angles, but we do know the reflexive property. So this would be side, 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 triangle, congruency theorem. Okay, and it's for the same reason in the sense that the reflexive property AC is congruent to itself. Okay, both triangles are sharing that line. All right, that line segment. So always be aware of the reflexive property, guys. It's always there sometimes, and it can be useful most of the time, honestly. All right, 22. Given that they are congruent, okay, so they go ahead and tell us that these two triangles are congruent. List all the corresponding parts. All right, here we go. So since they're all congruent, corresponding parts is kind of like a cough cough, CPCTC. So RS is going to be congruent to TU. SW is going to be congruent to UV. RW has to be congruent to TV. Okay. Don't forget the angles. Angle R has to be congruent to angle T. Angle S has to be congruent to angle U. And lastly, angle W has to be congruent to angle V. There we go. So again, corresponding parts of congruent triangles are congruent. That's the idea. Very important idea. All right, so properties of polygons. Right. So they tell us it's a parallelogram. They want us to solve for LM. And basically, what we know about parallelograms is their opposite sides have to be congruent to each other, not just parallel, but also congruent. That means LM has to be congruent to ON. Now, when you use their expressions, okay, you have to set it up like this. So LM is really 6x minus 7, while ON is 2x plus 9. So we're going to set them equal to each other. Solve for x. Okay, subtraction property, addition property. Okay, because we're isolating. Get 4x. 9 plus 7 is 16. Division property. X equals 4. Plug it back in. All right, plug it back in for LM. Honestly, it's kind of funny because you can plug it in for ON. It should be the same because it's a parallelogram, right? So LM should be 6x, which is 6 times 4 minus 7. You should get, I believe, 20. Um, wow, I'm tired. 28, 24. What am I thinking? Yeah, 12. Yeah, 12, 24 minus 7. That should be 17. You could always double check. Yeah, 17. There we go. 17. Yep, 17. There we go. All right, solve for the y value. Okay, if you notice, OL should be congruent to MN. So really, it's just MN equaling uh, OL, and that's really just y plus 3, and you're equaling it to 12. Subtraction property, and y equals um, 9. Yeah, so y equals 9. C, ignore that. Might be a typo. All right, so again, that was just the properties of a parallelogram. Okay, kites. Kites come after rhombuses, and the idea is that ST is going to be congruent to KS. So if it's asking you to find the value for KS, well, you simply have to look at ST, which is 2. Okay. Now solve for EK. Okay. We already said that this guy is 2 for KS, and all we have really is a right triangle. Okay. So how do you find the hypotenuse of a right triangle? That's Pythagorean theorem. So EK is really just going to be EK squared equals KS squared, which is 2, plus ES, which is 3, and we're just using Pythagorean. And then don't forget to square root both sides. So EK equals square root of 13. If you want, you can go ahead and approximate, get a decimal, that's fine. Okay. All right, number 25. This is kind of interesting because finding the area of a rectangle and a triangle is 8th grade. We know that the formula for an area for a triangle is really just length times width. We know that using the Cartesian plane, we have a 3 by 5 rectangle, and we all know that 3 times 5 is 15. So the area for that rectangle is 15. Now a triangle is a little bit more interesting. Our base, right, times our height, which is 6. Okay, I'm counting the squares, by the way, the tiles on the Cartesian plane. And our formula for a triangle, again, is 1/2 base times height, because it's really just half of a rectangle. So if we go ahead and follow through, we got 1/2 times the base, which is 4, times the height, which is 6. So we get 24 divided by 2, which is 12. So our area for our triangle is 12. Okay, so again, that was just math 8. And yeah, so that's why we didn't really go into it. That's actually kind of coming into semester 2 a little bit. But yeah, that's math 8. All right, exterior angles theorem. Okay, so good stuff. Solve for x. Now, what we should know is that these two remote interior angles should add up to the exterior angle. So we have x plus 46 should equal the 134 degrees. Go ahead and use the subtraction property. And we have x equaling, oh boy, I am tired. Let me try this in my head. 34, remainder of 12, 88. Yeah, double check for me. Should add up to 134. And I think I did it okay. But double check, but x should equal 88. Okay, sorry, I did some quick math off the top of my head. All right, so just remember the idea. The two remote interior angles have to add up to the outside. Same thing here, guys. The two remote interior angles have to add up to the exterior angle. So we have 6x minus 1 um, plus the 5x plus 17. And again, they all add up to the 126 degrees. Combine like terms. Okay, 17 minus 1, 16. Use your subtraction property. Oh, nice. And we should get 110. Division property. X equals 10. Solve for all the angles instead of solving for x. So that means we actually have to plug in 10 to get all our values. So that's really going to be 6 times 10 minus 1, which is 59 degrees. Okay. And then 5 times 10 plus 17 is 50 plus 17, which is 67 degrees. And you could always double check, um, add those two together, and they should add up to 126. If not, something's wrong. All right. Rotational symmetry. Nice. So using the shapes below to determine the following lines of symmetry and then angles of rotation symmetry. So if I was to fold this rectangle here, it would map onto itself. If I was to fold right here, it would also fold onto itself. So lines of symmetry, two lines of symmetry. As for rotational symmetry, remember, if you were to rotate, it was like this. It was like you have 360 degrees in a circle. You have how many lines of symmetry? Two. So in a sense of rotational symmetry, you have rotational symmetry of 180 degrees. Okay. So if you rotate it at 180, it'll map onto itself. If you rotate it at another 180, it'll map onto itself again. Now, as for this circle here, lines of symmetry, if I fold this star here, it would map onto itself. If I fold the star here-ish, it will map onto itself. If I folded it here, if I folded it here, if I folded it here, that would all work. So we actually have one, uh, two, uh, three, four, and five actual lines of symmetry. Okay, so five lines of symmetry. And again, 360 degrees divided by your numbers of lines of symmetry. And you should get, I think, 72. Wait. Yeah, 72 degrees. All right, for a rotational symmetry. Okay, I think that was earlier in the year. All right. So coming up on the last page, I believe, we'll complete the following proofs. So if we're looking at this one right here, we have AB. This is given. AB is congruent to DC. Okay, and they mark it for us. Prove that these two triangles are congruent. Well, they didn't just give us that AB okay, is congruent to DC. Yeah, they say it's given, and they have that little table right there. AC is congruent to AC. Well, anything congruent to itself is usually a cough, definitely using the reflexive property. And I think something's wrong with this table. Notice how we only really get this side being congruent to this side being congruent to itself, right? We only have sides given to us. Um, and that could be an issue. There could be something missing in here. We are trying to prove that these two triangles are congruent. They did give us these angles, okay? But remember what we talked about? Side angle is not a triangle congruency. So let's realize that these are actually right triangles that have the same leg and the same hypotenuse. So this is actually the hypotenuse leg triangle congruency theorem. All right. The giveaway was you had the right angles making them right triangles. Okay. So it's not supposed to be angle side. It's actually hypotenuse leg. All right. So moving on. They give us in this example, we'll call this example 2, I guess. PQ is congruent to RS. All right, they give us that. Then they say PQS is congruent to RSQ. That's nice of them. That's interesting. And we have to prove that these two triangles are congruent. So we get the side, we get this side, we get this angle, we get this angle. Already, I'm looking at the picture. I'm thinking reflexive property. Okay, so again, go off the picture, and that kind of gives you an idea on how to set up the proof. Now, I'll start with what's given. PQ is congruent to RS, and then that the angles PQS is congruent to the other angle RSQ. Okay, QS is congruent to itself. That's a reflexive property, so look at that. And if you look at what I marked up here, I have side, angle, side. Okay, side, angle, side. Okay, for my triangles. So these two triangles are congruent by the side, angle, side triangle congruency theorem. All right. All right, so I think these are the last two proofs. Okay, so I'm going to go ahead and go through them for you for your viewing pleasure. LM is congruent to NO. So they go ahead and mark them for us. All right, that was given. They're so nice. They treat me so fine. All right, and then angle M is congruent to angle O. Very nice. That was given. How nice. Um, so let me mark that. Okay, so that is that. So I got a side congruent to this side. I got an angle that's congruent to this angle. I do see vertical angles. Do you guys see that? I see vertical angles. Whoa. And that spells angle, angle, side. Angle, angle, side. So I think we're going to prove this by angle, angle, side. Let's see. So we got OPM, OPN, sorry, is congruent to angle MPL, and that's because of vertical angles. Okay, remember we talked about that. And then, hey, look at that, angle, angle, side already. So they basically just did the coup d'etat. This triangle, MPL, has to be congruent to the other triangle, NPO. And that is because angle, angle, side, triangle congruency. Very nice. All right, last one. Angle L is congruent to angle N. All right, let's make sure we mark that. So we got an angle. I got an angle. All right, angle LOM is congruent to NMO, angle NMO. So I got this angle, which is congruent to this angle. Okay, those were all given. And now I'm thinking, hey, don't I have like the whole reflexive property? Because those two triangles share the same line, right? MO. So this side is congruent to itself. So do I have angle, angle, side again? Looks like. All right, so again, angle, angle, side. So let's see. Let's start off with the proof. They tell us that L is congruent to N. That was given. Okay, then they gave us these angles. Angle LOM, which is congruent to angle NMO. Sorry, that's the worst NMO ever. Um, and then the reflexive property. Hey, look at that. So MO is congruent to itself. MO, reflexive property. And then finally, these two triangles are congruent because of, again, angle, angle, side, triangle, uh, sorry, congruency theorem. There we go. All right, guys. So that was the study guide. If you guys have any questions, get your practice in. All right. You just watched me go through this whole thing. Who knows how long your wow, that's a lot of work. But who knows how long you can watch me for until you start to understand. I do recommend that you guys start practicing your own problems. Go through your practice problems that I give you, that I assign you. It's worth your time. Okay. So this is a very well condensed review that I gave you. So please look through it, understand it, drop by if you have any questions. All right. Have a great night and good luck.